Hello everyone and welcome back to NL582 Modeling and Control of Electric Machines and Drives. Last time we was talking about the synchronous machine connection to the load. Okay, so we said that the synchronous generator connection to load. Okay, so we said that we have two kind of connection for the synchronous generator or application that can be used. The first one, what we called the standalone mode. Sometimes we call it the isolated mode. Sorry. Okay. So the standalone or the isolated mode, what we mean by it is just we're talking about a single synchronous generator feeding an isolated load. Okay, that is what I mean by this connection type, the standalone or the isolated mode. And we said those are mostly used for two kind of applications. The first one is the very well-known backup emergency generator. Okay, or the other one, which is the or the other application famous for this, is used for also remote areas. Okay, like we said last time, the backup generators mostly run by diesel power to generate electricity for the vital loads in case of losing the main power coming from the grid. So we use this kind of generators with this, or to some kind of remote areas, very remote from the public grid. Okay, the other one is the parallel connection. Okay, so actually the parallel connection, the most obvious one of it is the connected to grid mode, but also we can have two or more generators connected in parallel to feed isolated loads. Okay, so it is the same like having the single generator, standalone generator connected to a load that they remote from the grid or something, but now rather than having just one generator to feed it, we have two or more connected in parallel to feed it. So that means we have a higher load, a big load, than just the capacity of one generator. So we use more than one generator connected in parallel to just be able to meet the requirements of this kind of a load. So that's still parallel connection, but it's not connected to grid. Okay, so you have just two or more generators connected in parallel but feeding isolated load. Or the most obvious common one of them, which is the connected to grid. Talking about here the public grid, like is just typically we're talking about hundreds of generators in the very big grids, I mean, okay, connected in parallel. So it's just like what we said last time. It's just in the public grid we have many generators connected, and they are all sharing the load together, what we call a grid. Okay, we started talking last time about the standalone mode. Okay, and we just use the equivalent circuit and try to quantify what's happening with it and just log what happens if the load changes with this just one generator connected to it trying to feeding it. Okay, so that was last time when we just trying to talk about the just the standalone mode. Okay, So for here, or for now, we will just start talking about the parallel operation. Okay, so why actually we go to the parallel operation where we just have parallel operation? We mean more than two generators or more connected in parallel to feed loads. Why we just don't have a single generator for loads? So that means just for any area, maybe just a neighborhood of homes or something like that, we just having one generator to feed them. So for each small town we have just one generator to feed them, a big generator feeding them all, and just doing like that. We do not just connect them together, we don't have a grid. Okay, we just work with all isolated modes. So it's just we have a generator for each home, and each one of just every home it just work on its own generator. Why we are using a grid? Why are we using many generators connected in parallel to feed the loads together? Okay, so that we call it just the benefits of paralleling generators. The benefits of just having the generators connected in parallel to feed loads. Okay, so the first one is the redundancy. Okay, what I mean by this is if you lose one generator, you still have power from the others. Okay, that's very obvious. Rather than just using one big generator to feed all the load, no, have 2 or 3 generators working in parallel. That means if you lose one of them, that means you have a fault on one of them need to go to maintenance or something like that. So you don't lose all the load, but you just still have the other generators working and feeding the loads. Okay, at least a big portion of this load, so you don't just lose all of the connection, all of the power you have at one time. Okay, the other one is scaling. What I mean by that is it's more flexible. Okay, it's just more flexible to have multiple generators together rather than having one big generator. Okay, what I mean by here, it is just if you have some kind of a load, so you just get a generator that is good enough to feed the power requirements of this load. But what happens if this load increases? You need more power. So it's obviously, if you're just using one generator, one big generator, so you don't have anything but to get rid of the generator and get a bigger one, and that's not very wise, you know. So rather than having this, you can just have smaller generators and use 2 or 3 of them in parallel. So if you have increase in the load, you just get another one and connect it with them in parallel. Okay, the other thing to have, not just the flexibility just like that, is the logistics. The logistics are much easier and more economic. What I mean by this logistics is the manufacturing, transportation, installation, and all that stuff, okay, are more convenient for smaller generators. Okay, so Rather than just if you have some kind of a 1000 megavolt ampere load, a load that requires 1000 megavolt ampere. Rather than just having one very big giant generator that can handle 1000 megavolt ampere, that means this generator will be huge. Okay, it will be much more expensive and much more harder actually to manufacture it, to install it, to transport it to whatever location you want. It's just not convenient. Okay, so rather than just having one big giant generator to use, we use just multiple smaller generators. That will be much easier in all of that, in the manufacturing, transportation, and installation, and just use them together in parallel rather than just having one giant one. Okay. Number 3, resource management. Okay, what I mean by this? What I mean by this here is generators requires mechanical power to run them. Okay, we know that the generator needs mechanical power to run them. Okay, and this mechanical power comes most of the time from natural resources. Okay, I mean hydropower, wind energy, coal, oil, all that stuff that needs to just be converted into mechanical rotation used in the turbines. Okay, so these natural resources are not concentrated in one place. These natural in multiple places. Okay, so there's a place that have wind but don't have coal. The other one just have more coal to be used but doesn't have oil. Other places have oil. You know what I mean? So we cannot just have one big generator and just leave it in one place, because we will need actually so much more logistics to transport all kind of these resources to this place. But if we have multiple generators connected in parallel, that means we'll have a generator that's run by wind energy located in areas with having good wind. Okay, and other generators that run using oil, so it just positions near the oil fields. Another one using the hydropower located in a dam, so you can use the head of the water coming over the dam. Okay, so that's what I mean. Rather than just having one big generator and you don't know how to just get all these resources to it, no, we have different smaller generators distributed all over the country, and each one of them just making use of the natural resources available in each area, and you just connect them in parallel and you just use them as one generator. Okay, number 4 is efficiency. Okay, what I mean by efficiency is machines are designed to work more efficiently at or near its rated power capacity. Okay, so what I mean by this, again, back to the big example. If you having a big load of 1000 megavolt amperes and you want to feed it, and use one single big generator, that's a synchronous generator with a capacity 1000 megavolt amperes. Okay, but this loads, we're talking about a big load in a grid. That means this load does not remain like that. If you're just talking about a factory or something, so the factory are not working 24/7, some of them actually. Okay, so if it's not working like now, so you will not have this much of a load. If we're talking about more to understand the domestic loads, so our homes, we use much powers during the day while we are awake. Okay, but when we are sleeping, we don't use that much of a power. Okay, you don't use all the kitchen appliances, most of them actually. You use the fridge obviously, but you don't use something to cook while you're asleep. You don't use most of the lighting, all that stuff. So this load goes much down. So if you just designing this generator to work more efficiently at 1000 megavolt ampere, that means if you're using this generator to feed domestic loads, it will be more efficient working during the daylight, but in the night it will be much less efficient when you're working. Okay, that means, what I mean by less efficient, that it will use much mechanical energy to generate the required electrical energy. That means we will have much higher losses, okay? And we don't like this. So rather than just having something like that, no, we don't use one big one of this. Rather, we use just 3 different generators, okay? So if the load goes down, then you can just disconnect one of them and keep the other 2 working also at its rated capacity. You know what I mean? So like now, those 2 generators will be working at a very high efficiency, and you just switch it off, the 3rd one. But if you're using one big generator, you cannot switch it off, okay? Because you still need power. So this generator, if it is that big, will be working at what we call partial load. It's not feeding the full load it can feed. So it will not work as much efficient. Again, because we are just designing machines to be more efficient while working at its rated capacity, because it's more wise to do, okay? We're not having big machines to feed smaller loads. It will not be economic, it will not be wise, okay guys? Okay. So that's why actually you need to go with paralleling generator, not just have one big generator for each load, okay? So it's just redundancy, scalability, resource management, and efficiency. Okay guys, so we know now that using parallel generators is just more wise to go most of the cases, okay, unless you just need some sort of a backup generators to use in feeding a small load or something. So it doesn't matter to just use one generator. Okay, so let's talk about the parallel connection like we use here. Okay, so the parallel connection, like we said, have 2 types to look at. The first one is just you have 2 or more generators to feed an isolated load or connected to grid mode. So let's start with the first one, which is 2. It is just 2 or 4. So yeah, so let us just speak about what happens actually with just having the generator working in this condition. Okay guys, yeah, but let's say what will happen when you just connecting a generator, or so I'm talking here about one or few number of generator in parallel, okay, feeding isolated load. Okay, so here the parallel connection, just a few number of generators, 2 or more, 2, 3, 4, or even just having one, which is the isolated mode. But both of them talking about connection to isolated load, not in the public grid. So you just having a load you want to feed, okay? So that kind of a load here, impedance Z load, okay? And this Z load here, you want to feed it. So either you having one synchronous generator like this, a synchronous generator, to feed the load, if it's just the generator good enough for the load, or the load is just very small. But if you're having higher load, so you will need more than just one generator to feed. We connect them in parallel like this, okay? So whatever it takes. If you have a small load, you just have one generator to feed it, and it's okay because it's a very small load, you know. Okay, if it goes higher, so you need more than one connected in parallel because of all the benefits we said about the parallel connection of generators rather than having one big giant one, okay? So doesn't matter if you just have one or more in parallel, but the whole point is just we have an isolated load like that, we want to feed it. It's not like just talking about connected to grid mode yet, okay guys? What I'm trying to say here, what those generators, so one generator or even multiple generators connected together, will just react to this load change, how they will feed it and how the engineering of this goes, okay? So let me just start by saying this. Synchronous generators are required to generate both active power P, okay, in watts, and reactive powers Q. It's measured in VARs, volt ampere reactives. Yeah, let me make it in capital letters. Okay, that means you need the combination of Q and P, which is giving you the S in volt amperes, the apparent power. Okay, so like we said, it's an AC machine feeding AC loads most of the time, so that means you need to just feed the loads with its requirements, whether it's P and Q. So the generator has to just generate both of them. Okay, the active power, the physics of it, actually, the P comes from the input mechanical power. Okay, it's a generator. Okay, so it had an input power here, which is mechanical power, and you lose some of it as P loss. We talked about this and all components of the losses in this kind of machine, and the rest of it is the P output, which is electrical power in watts, like we said. Okay, so this P we are talking about here, that needs to go to the load with the load requirements coming from the mechanical power input of the generator. Okay, but what about the reactive power? The reactive power Q, again, it's physics, it just comes from the excitation. When I say just excitation, I mean field winding excitation, okay, what's giving you the magnetic field. Okay, so the reactive power that going out of the machine is just created by the excitation that goes to the field winding. Yeah, so here's the deal. If you need to increase the active power output, so that means this load here requires P load and Q load. Okay, so this, if it was just one generator, it has to feed it with both of them, the P and Q, or it is even multiple generators connected in parallel. Okay, so if the load requires more P, that means those generators, if there's one or more, has to increase the P generated of them to meet these requirements. Or if Q load goes up, that means those generators has to increase the Q generators to meet these requirements. Okay, guys? So here's the point to get in mind. The P comes from the input mechanical power. So if you need to increase the active power output of the generator because the load goes higher, that means you need to increase the mechanical power input. Okay? If you need to increase the reactive power output of the machine because the load requires more reactive power, that means you have to increase the field excitation of the machine. Okay? Talking about the field excitation, okay, if you remember, the field excitation is just related all the time with the induced EMF. Yes? So the induced EMF of the machine, of any kind of machines actually, equals K phi omega m. Yeah? Phi is the magnetic flux and omega m is the speed of rotation and K is just a constant. Okay, guys? So it's not also talking about here the field excitation is controlling the amount of reactive power, but because here the field, it also controls the induced voltage, which controls the terminal voltage. Remember, that is the RA, JXS, and here is E. Armature, okay? And that is the terminal voltage here, that is IA. And V terminal, actually the terminal voltage of the generator we're talking about, equals EA minus IA and RA plus JXS. Yes, guys? So how much terminal voltage you need? You have to control EA. So that's what I'm saying here. The reactive power Q is totally related to the excitation, or coming from the excitation of the field winding. And the excitation of the field winding controls the magnetic field. So if you want to increase or reduce the reactive power out of the machine, you have to increase or reduce the field excitation, which increases or reduces the magnetic field, which is in turn increases or reduces the induced voltage, which is in turn increases or reduces the terminal voltage. It's coming from this. Okay, guys? That means you have a direct relationship between the terminal voltage of the machine and the Q output of the generator. That's what we're saying. Because the Q output of the generator, if you want to control the Q, like we said. So the Q generated, if you want to control it, that's coming from the excitation, the magnetic field. Okay? They are just related together. And this magnetic field, when it's controlling or changing, it changes the induced voltage with this. Okay? So that's coming from this. The Q comes from the field. But changing the field changes directly the induced voltage. And changing the induced voltage in turn changing the terminal voltage. So you have a direct relationship between Q and the terminal voltage of the machine. Okay, guys? So that's taken us to what we call here the VQ relationship. The terminal voltage relationship with the Q generated of the machine. If you plot them together, it will give you something like that. That is the terminal voltage of the machine, and that is the Q generated out of the machine. Q generated is the one supplied to load, okay? So if the load requirements goes up, that means the Q of the load goes up. The load requires more reactive power, more Q, so the generator has to just generate more Q like this. And if you generate more Q, what happens is you start decaying like this, remember? So at this point, that is the no load, okay? That means you're generating zero reactive power. That's what I'm saying. So this point is just corresponding to the V terminal at no load, which is equals EA directly, remember. The terminal voltage at no load is EA. If this current equals 0, that means the terminal voltage equals the induced voltage, okay? But while you try to increase the Q out of the generator until you hit this value, which is QFL, FL means full load. So that means that is the full load the generator can go. So that means that is the rated value. The generator cannot go beyond this value, okay? So that means at this point here, your terminal voltage will decaying. That is V terminal at full load, or let me call it V full load at this point. Okay, guys? So the voltage has just decayed from this value to this value, the no load value to the full load value. Okay? Because it's all like that. It's all like what we are saying here, guys. Yeah? That means you're just supplying more reactive power out of the machine, and that means the terminal voltage will just start decaying. Okay? The more Q generated to load, the less terminal voltage VT happens here, okay? That means if the Q load goes up, that means the Q of the generator has to go up to meet it, okay? And this will result in a reduction in the terminal voltage. V terminal will go down, okay? But we do not need this. That's not good, okay? Because like we said last time, We don't like the terminal voltage to change because most of our loads are just sensitive to change in the load, and that may damage those loads actually. What to do to compensate for this reduction in V terminal? Okay, what we need, or what we do here, is to compensate for reduction in terminal voltage. We increase the induced EMF EA by increasing the field excitation. That means increasing the magnetic field. Okay guys, remember EA equals K phi omega M. So if the terminal voltage goes down, and you need to increase it back, because go back again to this equation here, okay? That is terminal voltage equals EA minus IA multiplied by RA plus JXS, okay? So what happens here is you will need to supply more active power of the machine, and this will result in a reduction of terminal voltage. How to just get it back up is just by increasing this EA up from this equation like this. And how to increase EA, go again to this equation. It is how to calculate EA. Okay, you can increase it using increasing the magnetic field or increasing the speed. We don't want to play with the speed, and we'll just say why in a minute. Okay, so we need to increase EA, so we increase phi, increase the magnetic field, by increasing the field excitation. We just push more voltage to the field winding, and this will just increase the excitation. Okay guys, so it's again here to the same thing. The terminal was Q generated. Okay, so that was our curve like this, yeah, and that was the Q full load we're talking about. Okay, so that was the value here where the voltage just came down. Okay, that is V full load. I'll call it V full load 1. It just decreases from this value, V no load. If you want to restore this value back, because we now need the voltage to go down to this point, V full load, what will happen is we will increase the excitation. We will push the field up by increasing the excitation, and this will increase the induced EMF. Okay, and increasing this will be just now working at a different curve, which is this curve. Okay, so increasing the excitation like this will change to be this one now. By seeing here now at the same Q full load, you get back to the value of the voltage, which was no load at the first one. Okay, so this becomes your V full load 2 after increasing the excitation. Okay guys, this exciting action is done by a nice controller we use with the synchronous generators. We call it the AVR, automatic voltage regulator. Okay, what this automatic voltage regulator do, it basically senses the reduction in the terminal voltage of the machine and adjusts the excitation of the field winding to restore the terminal voltage to its previous value. Okay, so it's kind of a controller used in the synchronous generator that's using this. Okay, it just have a sensor to measure the voltage out of the generator and try to keep it at this value. So if it goes down, it increases the excitation to push it up. If it goes up, it reduces the excitation to bring it down. Okay, so that in the first control system we will just talk about in synchronous machines, what we call the AVR, the one that is responsible of keeping the terminal voltage of the machine at the rated value of the machine and keep it like this. Okay, by controlling the excitation. So the automatic voltage regulator will sense the terminal voltage. If terminal voltage goes up on its value, it will reduce the excitation to bring it down again. If the terminal voltage goes down, the AVR will bring the excitation up to bring the terminal voltage up again. Okay, guys? Good. Speaking about this, we need to identify a very, very important quantity in all kind of a generator. Okay, we call it the voltage regulation. Okay. The automatic voltage, the voltage regulation we're just talking about here is a very important relationship. So voltage regulation, we call it VR most of the time, okay, equals this relationship, the no load voltage minus the full load voltage divided by the full load voltage, and most of the time it's a percentage value, so you just multiply it by 100, okay, to get it as percentage. So it's a very, very important quantity for any kind of a generator, and from here is just giving you an idea about how much the voltage of the generator will drop, okay, if you just connect the full load. Okay, so like you see in here, it's just subtracting V no load minus V full load. Okay, that is the very relationship we talked about. So that is terminal voltage here, and that is Q generated, and that was the reduction. Okay, so that means that is no load here, and for here is a full load. Okay, so that is a voltage at the full load, V full load, and that was the voltage at no load, V no load. So like you see, with the increase in the load from no load to full load, the voltage drops from V no load to V full load. It's unique for every kind of a generator, or for any generator, just to see how much this reduction, if the voltage increases from the no load to the full load, how much the voltage, the load, so if the load increases from no load to full load, how much the terminal voltage will drop. Okay, guys? Or sometimes we just understand it the other way around, because the natural operating condition of any kind of machine is to be working at full load, like we said before. So we don't leave the machine working at no load. It doesn't make sense. So the machine typically works at full load at this point. Okay? But now we are saying, what happens if we lost the load? So all the load have been just suddenly disconnected from the machine. So it is working primarily at this full load, this point, so that's the voltage, V full load. So if the load has been lost, all of it, the voltage will jump to this value, the V no load. Okay, so it will also like this. So you can understand voltage regulation. It is any one of them. How much the voltage of the machine will be reduced if you increase the load from no load to the full load, or how much the voltage of the machine, the terminal voltage of the machine, will increase if you just reduce the load from the full load to be no load at all. Okay, guys? So that is a very important quantity to be determined for any kind of a generator. Obviously, the better the generator, the less this value. So if you have this voltage regulator less and less, that means you have better generator. Okay, it's a design factor. It's something related to the design of the machine itself. So if you can design a machine that having a less and less voltage regulation, that means the voltage does not drop that much with the increase in the load. Okay, guys? Okay. So that was the VQ relationship. In the same order of this, I'm going to be talking about now the FP relationship. Okay. What is this FP relationship? Now, like we said before, what happens if the reactive power requirements of the load goes up? If QL goes up, what happens? That was how we just understand the VQ relationship. But here, what happens if the P goes up? If this load you are trying to feed now, the load requires more, so that is P load now. That is the one that is increased. Okay, that means the generator you are just attaching here with is one generator or multiple generators connected in parallel, they will need to increase their P generated to just meet these requirements of the load. Okay guys, so if P load increases, your P generated has to increase to meet this requirement. Okay, what happens if your P, the active power, increased? Okay guys, active power increase like this, or the P load is just going up. Like we said before, more load on the shaft of the machine, that will be directly translated that you have more counter torque on the shaft. Remember, you have a generator, that's the generator shaft, and it goes like here at the torque of the mechanical torque applied. Okay, the mechanical torque, the external mechanical torque applied to rotate the rotor in this way, that is omega m. Okay, so if the load goes up, the P of the load goes up, that means this counter torque, remember there is a counter torque here internally in the machine, okay, will increase, and that acts as a brake. Okay, so if the P of the load goes up, that means you have more load, and that acts like a brake on the shaft, because the counter torque internally in the generator increases. Okay, and this will result in reduction in speed, because this acts like a brake like this. Okay, this acts like a braking action, so the speed drops. Okay, like we said before in DC generator and everything. But what do we mean by a speed drop here? Remember, we'll talk in here about a synchronous machine. For a synchronous machine, okay, the speed is synchronized with frequency. Remember, ns equals 120 f over p. That's the speed of rotation for a synchronous machine, and s, and that's the frequency. They are directly related to each other. So if you have an increase in the load, the speed will drop, and if the speed drops, the frequency drops with it. Okay guys, and that's why we're saying we're talking about the FP relationship, the relation between the frequency and the power, because increasing the power of the machine, because the load increases, will just drop the frequency, because the speed will drop with this. Okay, so if we try to plot it on the same way, that is the n, the speed, I'm calling it n RPM just to have it in mind. Okay, or let me call it ns just to make it unique for synchronous machine. Okay guys, and that is the P generated. What happens is again the same idea. With the increase in power, the speed drops. Okay, so this here, the no load value, P no load, and with the increase until you hit here, which is the P full load, the full load the machine designed to work at. So at P no load, this was the speed, and no load. Here at full load, the speed drops to this value in full load. Okay, and if you try to plot it with the frequency to give you the FP relationship, it gives you just a similar curve, because you know the frequency and the speed are just synchronized, so whatever happens here is just mirror image there. Okay, so that is P no load, and that is P full load. Okay, that was the frequency at the no load, which is higher like you see, but with full load the frequency drops. This is value because the speed dropped from no load to full load value. Okay guys, so like what we talked about before in the voltage, when we define the voltage regulation, now we having the same idea because the speed or the frequency goes down here. Okay, so we define another term here, we call it the SD, speed droop. Okay, speed droop equals n no load minus n full load divided by n full load, and if you wanted a percentage, multiply by 100. it will give you exactly the same value if you use the frequencies. F no load minus F full load over F full load multiplied by 100. Again, it gives you an indication of how much the speed of the machine will drop if you go from no load power to full load power. So the speed will drop from no load to full load. Again, it's unique for each machine. Again, the same idea, or the frequency. How much, when you just increase the power from P no load to P full load, how much reduction will happen in the frequency? Okay, or again, you can understand it the other way around. If you're working at the full load, because that's the typical working condition of the machine, so the speed you're working at will be that speed. If you lose this load at all, so you're now working down at P no load, the speed will increase from the full load value to no load value. And the same idea, the frequency will goes up. So the speed droop gives you this indication. How much reduction you'll have in the frequency of the machine. Okay, when you just having an increase in the load from the no load to full load, or how much increase in the frequency of the machine when you just lost all the power you are just putting to the load, and you was working at the full load, and now you just doesn't supply any power, you don't have it, it's no load condition. Okay guys, so that's what happens here if you increase the power, because the power of the load P, the active power, goes up, the frequency will go down, and that's not a good thing. Again, remember when we talked about the terminal voltage here, we said that we use an AVR, automatic voltage regulator, because we don't like the terminal voltage of the machine to keep swinging up and down with the increase and reduce in the requirements of the reactive power of load. Okay, so we use the AVR as a sensor which controls the excitation, the field excitation, which controls the magnetic field, to just restore back the terminal voltage to its rated value with the this change happens in the load. Okay, so it's the same idea here. What happens if the active power requirements of the load changes, it will impact and change the frequency of the machine, and we don't like this. Okay, we have to maintain the frequency output of our machine at its rated condition. For here in North America, we're talking about 60 Hertz. So we need to maintain it 60 Hertz, otherwise it will harm the loads connected to the generator. Okay, so like we had an AVR, an automatic voltage regulator, to just sense the change happens in Q requirements and restores the terminal voltage back by controlling the excitation, we will have another something here, another controller here. We call it the governor. Sometimes we call it the AGC, automatic generator or generation control. Okay, so yeah, they have just the same, so it's the governor or the AGC, both of them stands for the same exact thing. Okay, it's a controller, senses the change in frequency which happens by change in active power requirement or generation, and adjusts the input mechanical power to restore the speed and frequency back to its rated value. Okay, so the same idea, but you know here how to actually control the speed of the machine here and all that stuff, as you control it by playing now in the mechanical power input. Remember, it's the same idea, because the whole point is you have an input mechanical power from here to the generator, and you lose some of it, and the rest goes out to the load. Okay, that is the generated, or that's going to, yeah, that is the P generated going to the load. Okay, if this goes up, like we said, the speed will go down unless you increased this P input, the mechanical power here. Okay, guys? So what happens is your P load goes up. If it happens, the speed will go down, and that will bring the frequency down with this. Okay? So here, stepping in the governor, okay, which increases the mechanical power input of the machine, and this increases back the speed and increasing back the frequency to its rated value. This guy, we call it the governor. Okay, so the same idea that happens before here. If this was the N no load we want the machine to work at, but with increasing the load from no load to full load, so the speed drops to this value, N full load, and we want to restore this N no load back at the same full load power. So what happens? You with the governor, which increases, the governor goes N to increase the P mechanical up, and this will bring you the curve up to this point. Okay, which restores you back the N no load. Okay, guys, so the governor actually raises this curve, this NP curve or FP curve, from this point up to this point. Okay, guys, that's what's happening here with this kind of operation. Okay, so here we are now talking about the second controller used basically with the synchronous generator, which is the governor, which is controls the amount of mechanical power goes in the machine to adjust the speed or the frequency. So it has a sensor that senses the actual frequency output of the machine right now and just adjusts the mechanical power up and down to restore back the frequency. So the frequency goes down, it increases the mechanical power to bring it up again. If the frequency goes up, it reduces the mechanical energy to bring the frequency down again. Okay, guys? Again, it's the same principle. What controls the frequency is the power. So you increase or reduce the mechanical power to increase or reduce the frequency. What controls the terminal voltage of the machine is the reactive power, the Q, which comes from the excitation. So you increase or reduce the field excitation to increase or reduce the reactive power, which is increase or reduces the terminal voltage of the machine. So we have two controllers using here with the synchronous generator, the AVR, which holds the terminal voltage at its rated value with any change in the load by controlling the field excitation, and the governor, which holds the frequency of the machine at its rated value with the increase or reduce in the load requirements by controlling the input mechanical power. Okay, guys, that's what's happening here. If you have one or more generators just connected to give power to an isolated load. Next time we'll take this to the highest level and talk about what happens if we are trying to connect in our generator to the public grid, where it's just very, very high number of generators are connected in parallel to just feed a whole entire grid. Okay? Thank you guys for joining me today, and I hope to see you next time.